Hello students, welcome back to our channel. So students, in last lecture we have seen what happens when a single inductor, a pure inductor having zero resistance is connected across an AC source. Now we will see what happens when a capacitor is connected across an AC source. So this is our circuit. And a capacitor is connected. This is the capacitor which is connected across right. So we have applied an alternating voltage source. We have applied an alternating voltage which is V naught sine omega t. Okay. So at any instant, if Q is the charge stored by the capacitor, so we can say that Q equal to CV, right? We all know that this is the equation which connects C, V and Q for a capacitor. So we can write Q equal to CV, and in place of V, okay, you all know what we are doing here. I am assuming that you have seen the lectures before this one, because you will understand the concept only if you see all these lectures in the order, right? So if you have not seen those lectures, so you are going to find some difficulty in understanding the concepts of this one, but I'll try to make you understand things a little bit more better. So what we are doing, that we have applied a voltage across the component, right? And using an equation, we will find the value of current, and then we will see what is the phase difference between the current and voltage, right? This is what we are going to do, and for this we are doing a very important derivation which comes in board exams and school exams, and during this derivation we are going to get some important new physical quantities and important formulae on which you have to practice some important numericals. So okay, we all know that Q is equal to CV. So if we put the value of V, C into V naught sine omega t, right? But we have to find the value of I, and now we have Q. So what we will do? How we can find I when we have Q? Obviously by differentiating Q, because I is what? I is dQ by dt. Now if we differentiate this, we will get I, which is equal to dQ by dt, right? Okay, what is the derivative of this one? Now first we will write it like this. Now let us find the derivative of this one. So what is the derivative? CV naught is constant, so it will come outside the bracket. And what is the derivative of sine omega t? Derivative of sine omega t is cos omega t into omega, right? Derivative of sine omega t is cos omega t into omega. So what we can do, we can write it as V naught divided by, and we can shift this omega and c on in the denominator, right? Like this, because if it will go in the numerator, it will come in the numerator like this, omega into c. So we can shift it like this, right? Into cos omega t. Okay. So if we want to compare V and I to find the phase difference between them, first of all, I should have sine theta, because only we can easily compare the phase difference between V and I when the equation of I will have sine theta in it, because equation of V has sine theta in it, right? So and for some time, let us substitute this one and let us write this whole thing as I naught, as we did in the last derivation. But as I have told you in that derivation also, that we cannot blindly substitute I naught in place of this. We will prove shortly that this is actually equal to I naught. But in a short while we are going to prove this. But first let us substitute this as I naught. So I equal to I naught, and in place of sine omega t we can write cos pi by 2 plus omega t, because sine 90 plus theta is nothing but cos theta, right? If you know a little bit of trigonometry, then you know that sine 90 plus theta is cos theta. So we can say by interchanging these two, because this is a plus sign in between them, so a plus b is equal to b plus a. So if we write it like this, if we write it like this, I equal to I naught sine, instead of pi by 2 plus omega t, we write it as omega t plus pi by 2. And now we can clearly compare the phase difference between V and I. So it is very clear from these two equations that the phase difference between V and I in this case is pi by 2, and current leads the voltage by pi by 2, because in this case we have plus pi by 2. In inductor it was minus pi by 2, so current was lagging behind the voltage. But in this case current is leading the voltage, right? Okay. Now before going ahead, let us first discuss this thing, that why we have substituted I naught in place of V naught upon 1 upon omega c. Since we know that I naught is V naught by R, right, where R is resistance. So if we can prove that 1 upon omega c is a term of resistance, then obviously in place of V naught upon 1 upon omega c we can substitute I naught. But how we will prove that it is a term of resistance? Let us take this term and put the values of all the units of all the physical quantities which are appearing in this equation. So the unit of omega is 1 upon second, and what is capacitance? C. Capacitance is Q by V. So what is the unit of Q? The unit of Q is coulomb and the unit of V is volt. Now again let us solve this. What is coulomb? Coulomb. Charge is current into time. So in place of coulomb, let us take this V and S in the numerator. And in place of coulomb, we can write current into time, that is A into S. Now S and S get cancelled out and we are left with V by A. V by A means voltage by current, and by Ohm's law, voltage by current is nothing but resistance. So the unit of 1 upon omega c is ohm. That means it is represented some kind of resistance. So we can substitute I naught in place of this thing. But what does it represent? 1 upon omega c is a very important physical quantity in this case, and that is represented by Xc, whose name is capacitive reactance. Name of this quantity is capacitive capacitive reactance, right? This is a quantity which is responsible for the opposition offered by capacitor to the flow of alternating current. More is the value of Xc, more resistance or opposition the capacitor will offer to the flow of alternating current. And obviously this is inversely proportional to the frequency. So if we increase the frequency of alternating current, then the value of Xc will decrease. So more and more current can pass through the capacitor, right? But if we decrease this value, then the capacitor resistance, the capacitor will offer more resistance to the flow of alternating current. So if in case of DC, DC means direct current, right? For DC, since frequency is 0, so omega is 0, so we can say Xc is infinite, right? So a capacitor offers infinite resistance to the flow of direct current, which means a capacitor blocks direct current. A capacitor blocks direct current, right? So the most important line, we will write it here, that in case of a pure capacitor means a capacitor whose resistance is 0. Obviously, the plates of the capacitor are made up of a metal, and all metals have resistance. So there will be some resistance of this capacitor, but we are ignoring that capacitor. So in that case, the capacitor is called an ideal capacitor or pure capacitor, right? So in case of a pure capacitor connected to an alternating voltage source, current leads ahead voltage by pi by 2. Current leads ahead voltage by pi by 2. Now let us make the phasor diagram of this. Let us make the phasor diagram. So this is Y, this is X, and this is the voltage. This is voltage V, and current leads the voltage by pi by 2. So this is going to be the current, right? So if this angle is omega t, so this angle is omega t plus pi by 2, right? Okay, now let's mark the other things. This is the instantaneous value of voltage, this is the instantaneous value of current. So this one is V naught, so this one is V naught sine omega t, this one is I naught, so this one is I naught sine omega t. Now let's make the graph of voltage and current. So if we draw the voltage like this is the alternating voltage V. So this is the angle pi by 2, right? And this is pi, this is 3 pi by 2, this is 2 pi. So the current leading the voltage, the alternating current is leading the voltage by pi by 2, and the peak value of current is less than the peak value of the voltage. So let us start it from here, because when the voltage was 0, then the current was maximum, and when the voltage was at pi by 2, when the voltage was 0, had 0 phase, then the current had pi by 2. And when the voltage had pi by 2, then the current had pi. So we can draw it like this. Right? So this is the peak value. This is the peak value of the voltage, and this is the peak value of the current. So this is I naught, and this is your V naught, and this is V, and this is I. So if we have drawn this graph of V and I with respect to time t, then we can mark these points. This is 0, and this is t by 4, this is t by 2, this is 3t by 4, and this one is t. Right? So this was everything about a circuit in which a single capacitor is connected across an alternating current source. I'll meet you in the next lecture. Till then, all the very best.